got a vision of a residential dwelling that's in the Pebble Beach area looking out towards the Pacific Ocean. Beautiful views that we've got through here through these windows, and yet we need to have a structural system that will be able to resist the potential code level seismic forces that is in this particular region. And so with all these big open window spaces, you can't use shear walls, which is typically what happens in a house, that the stud wall construction and the plywood sheeting or oriented strand board sheeting will provide a shear wall effect for the vertical elements in the lateral force resisting system. But of course you don't want to have solid walls when you have these potential beautiful views. So what do? Well, one of the approaches that you could take is a moment resisting frame. So that middle window that we were looking at is actually looking out right through this area, and here's this portal frame. Now in this particular one, it looks that the column and the beam are all of the same sizes. Of course here we have rigid joint construction. These little plates that make up what looks like a square there are continuity plates, and they're there so that the moment can get transferred all the way through the flanges, across the web to the far flange. You need those typically in these kinds of beam column connections. So we're going to take a look at the portal frame and get an estimate of what the response is under a seismic type of situation. We need to have not only strength of all the beams and columns, but we also ultimately have to have appropriate stiffness, right? Because remember, there's a big window in here, and if this drift gets to be too large, we'll start racking that window, and that window will begin to break up, and people don't like that either. So even if it was strong enough, then other brittle elements may crack up. So we'll deal with the stiffness at another time. Right now we're going to focus on what the strength demands might be if this lateral load were 10 kips, that tributary load coming into this particular frame, right? And we're going to take an approach with the portal method that is an approximate method, that if we guess the right things, then yes, we would end up with something exact. But usually what we're going to do is we're going to make guesses about the inflection point locations in the columns and potentially then also in the beams. Right? So if we guess that the points of inflection are at the mid-height of the columns and at mid-span of the beams, look what we end up developing here. That when we put the lateral load of 10 kips on there, we can then go look at a whole variety of different free body diagrams that are simplified by our assumption of the location of the inflection points. So let's go and draw then, for instance, this little piece here. It's 10 foot wide, so if we're guessing that the inflection point is at 5 foot for the beam, then that little segment is 5 foot long. And since the columns are centerline dimensions 4 foot or 8 foot high, then a mid-height assumption then puts those at 4 foot. Since we've guessed where the inflection points are, that's the locations of zero moment, so all we have then are shear forces and axial forces in the members to draw in that free body diagram. Right? And so on the left, there's our axial force in the column, there's our shear force in the beam, and then we have a corresponding set of shear and beam forces in the or axial forces in the beam. So let's look at what happens here. If we were to some moments about, say, this midpoint, hey, let's give these points some names here. We got A, B, C, and D there. Let's call this A prime, let's call this C prime, and let's call that D prime. I skipped B prime, I know, for no good reason. I just had to come up with some names here. If we sum moments about C prime, then notice we'll have 4 feet times V minus 5 feet times N is equal to 0, so that the axial force is equal to 4/5 of the shear. Now that tells us a relative value, doesn't tell us the value of the shear. Right, so one other thing that we are going to do is we're going to assume a distribution of the lateral forces. Now with only two columns in the system and with the columns being identical, then what we'll do is say, right, the columns are identical both in their size and in their end conditions, so they have the same stiffness. And particularly a shear stiffness. And what that means is that at the base of these columns, down here where these reactions are located, then those columns will pick up the same shear force. Right? So that's going to tell us then globally we've got then sum of forces in the x. We've got 10 minus 2v equals 0, so therefore v is equal then to 10 over 2 or 5 kips. So if that's the case, we can now feed that back over here and get the axial force is equal to 4/5 of 5 kips, or of course 4 kips. So that tells us then we've got a tensile effect over here on the left of 4 kips. That shear force was equal to 5, that's equal to 5, and then sum of forces in the y, then that axial force on the other side has to be in compression for 4 kips. And the only thing left then would be to find the moments at the base of each one of these columns. Now they're identical, and so since they're identical, the moments are going to be the same on both. And let's just choose this left-hand column. You turn the axial force around, you turn the shear force around at 5 kips. Shear force at the bottom is 5 kips. And then we've got our axial pull-out force, in this case of 4 kips. And your bending moment down at that base then is just going to be the 5 kips times the moment arm, which is 4 feet. So that will be equal to 5 kips times 4 feet, or 20 kip feet, acting in a counterclockwise fashion at the base of the column. So that gives us the reactions of the system. Let's just repeat them in a big way here. We got equal opposite axial forces of 4 kips each. We have 2 shear forces acting to the left at 5 kips each in response to this 10 kip lateral load, and then we've got our bending moment of 20 foot kip on both of the columns. Right? So there's your answer to part A. Now part B is go draw the shear and moment diagrams. Now we don't have any applied loads to any of the members, so all the effects are coming from that joint force. And what we can do in a sort of a variety of ways is we can sort of notice the pattern that we have here. And that pattern is that we've got 20 kip foot acting in a counterclockwise fashion at the base. So it points, when drawn the way we've got it, it points to the side that the moment diagram is. It points to the compression side. We know it goes to 0 at the midpoint. And notice we've got the same shear, same moment arm, so 5 kips times 4 foot kip, or 4 foot, to get to 20 kip foot at the top, and it's going to be in the opposite side. So there's 20 and 20 there, and you turn the corner, and you got to have for equilibrium the same. When you only have those two members framing the into the joint, they got to be the same. But notice what happens here. We've got the 4 kips for the axial force in the column becomes then 4 kips going in the other direction for the shear in the beam at the midpoint, and 4 times 5 is sure enough 20, and it's acting in a way that would create smiley face over here at that point. So that's exactly what we've got there. And again, by all of that, it's not really symmetry, but you could argue based on symmetry you've got this reverse curvature in the top of the column, and so we've got 20 down here. It's frowny face, so 20-foot kips. Let's put the units on there, and likewise you're going to end up with the other column being just the same as the left column in this instance. Notice it's not really symmetric, but it is identical situation. All drawn on the compression side of the member, so our curvatures are going to look something like so, which is exactly what we've got up here. The curvatures meeting the boundary conditions, all double curvature everywhere. You got something that's really not quite smooth right at that location. It could be smoother, but overall a nice little reverse curvature. No shortening of any of the members, so delta B has to equal delta C in terms of the lateral motion, so that the beam doesn't shorten, and delta B or B and C have to translate directly sideways in order for the columns not to. And there you go, there's your composite of the reactions, the final moment diagram, and of course that deflected shape that goes with that portal frame.